is Mr. Yeager. We are looking at rotational kinetic energy now. Trying to show a couple types of problems that come up that I know are a little bit difficult if you haven't seen them before. First, the question I have is basically a conceptual question, okay? What I'm looking at is I have these two objects, and I'm going to say they have the exact same mass m. So m is equal, okay? Equal mass, and they are basically launched down this inclined plane, and both inclined planes in this example are at equal heights, okay? So equal height release, okay? And the surfaces are, I'm going to say frictionless. I know that's kind of already a little bit irritating. What we're doing is we're going to ignore any energy lost through friction. Obviously, some people, if they remember back to a much earlier unit where I said, in order to roll, there must be some sort of friction, okay? But I guess we'd say basically friction is negligible, but an object can roll. So friction is negligible. Let's say that, okay? But it's enough that it can make the object start rolling. In other words, I don't want you to tell me that's friction that's causing a difference in this answer. Okay, friction is not important. So these two objects are released from the same height or the same mass. The thing is, the top object will slide, the bottom object will roll. And so my question is, which object should reach the bottom of the ramp first? Okay, which one will reach the bottom of the ramp first? So if we think about this problem early on, okay, whenever we see this type of setup, we need to think of energy. This is related to an energy type problem, okay? Not a momentum problem, not a force problem. If I'm interested in what's happening by the bottom, I'm interested in energy, okay? In energy. And I say, which one will make it down there first? The thing is, that's going to be related to velocity, okay? So again, technically I'm solving for time, but in relation to that is velocity. In other words, which one is going faster at the bottom, okay? Which one is traveling faster? So the thing is, if I look at this from an energy perspective, both these objects have a gravitational potential energy, they're starting at rest, of mgh. So they both have the exact same amount of gravitational potential energy, mgh. The issue is, what is that gravitational potential energy going to change into as it goes down and it finally reaches the bottom? Again, I'm only interested in the top and the bottom, okay, is really what we're looking at there, all right, right at the bottom, all right. So if I go through this, most people go, well, it's going to change into kinetic energy. Absolutely. But now, we have more than one type of kinetic energy, okay? What type of kinetic energy? Well, this one's just sliding, so this is going to change into kinetic energy translational, okay? Which is the 1/2 mv squared formula. Again, that is the energy of the object actually changing position. That's where what's translational kinetic energy is, changing position. Well, this object's also changing position. It will have kinetic energy translational, but what's this object also doing? Some of that energy has to be changed into rotational kinetic energy. And now we have basically the justification for our answer. Which object will reach the ground first? It's going to be the one that slides, because all of that energy, the gravitational energy, is changing into movement, linear kinetic energy, translational kinetic energy. While this gravitational potential energy has to change into both of them. Okay, it has to change into translational and rotational, which means the velocity of the rolling ball is less than the velocity, the linear velocity of the sliding block. All right, so that is something we have to pay attention to now. Okay, I'm going to skip a page. What we're looking at now really is the fact that we have this work energy theorem. Kinetic energy rotational plus kinetic energy translational plus GPE equals GPE plus kinetic energy translational plus kinetic energy rotational. Again, this side's final. This is initial. All right. Doing this problem, the object's not moving initially. Either it's not moving or rolling or rotating. So everything's just gravitational potential. It's on the ground at the end. It's just whether is it rolling or is it all changing into translational energy. But this is our new work energy theorem that we're talking about, okay, to be aware of. So that's one question. That's kind of more just conceptual. This one has maybe a lot more pieces to it, okay? Basically similar problem. I have this object. It has a mass m. I'm going to go and say it's a sphere. So I'm going to go and tell you that the rotational inertia for a sphere is 2/5 mr squared. Okay? So it's a sphere. It has a mass m. It has a radius r. Let's just say it has some radius r. Okay, that's the radius, obviously, of the sphere itself. Okay? It's initially at the height. We're going to say friction is negligible. All right? But it will roll. The object will roll. My question is, what's the velocity at the bottom? What is the linear velocity at the bottom of the slope? Okay? Give me a second. All right. So, let's try to figure out what's the linear velocity. This is an energy problem. So just like I did on the prior page, this is going to be gravitational potential energy initial, changing into translational kinetic plus rotational kinetic. All right. So let me write out my formula. I'm going to say I give you all the information. I'm going to say I'm going to give you mass, I'm going to give you height, and I'm giving you r. So you know what the r is as well. So I'm giving you all that information, and obviously the object's on Earth. All right. I want to see whether we need all of that. Okay, is all of these numbers important? What if I don't have some of these numbers? Am I still going to be able to solve? So let's go through it. So I have mgh equals 1/2 mv squared plus 1/2 I omega squared. That is the formula for rotational kinetic energy. So can I eliminate mass right now? The answer is no. It's not everywhere. It is not everywhere. But this is what I'm trying to work on. I want to change this into another form. I basically want to isolate velocity by itself, okay? And the thing is, I did not give any information about the rotational velocity of the object at the end. So I don't know what omega is either. So there's lots of stuff that I'm like, ugh, this is going to be tough. So what can I do? Well, what I basically need to do is I want to change I and omega to something else that I can then basically relate back to the other forms. So I'm going to do mgh equals 1/2 mv squared plus 1/2 parentheses 2/5 mr squared omega squared. I'm going to leave it like that for now. I'm going to take it step by step. Right there, what do you now notice? What can we now do? We can eliminate mass. The mass of the object is actually not going to help us at all, surprisingly, with the finding the velocity at the bottom. So even if velocity is mass is given, it's not important at all. All right, I'm going to bring this down here. So now I'm left with gh equals 1/2 v squared plus 1/2 2/5 r squared times omega squared. Well, what can I change omega into? Omega equals v over r. So this would be v over r squared. Got to make sure we realize this is squared. So what does that mean? I'm going to change it right here. I'm going to go right back to that. I'm going to square all the variables underneath. That means this is v squared over r squared. So look at this. This is 1/2 times 2/5 r squared times v squared over r squared. R squared cancels out. We don't even need the radius of the object. Like, this is crazy. We don't even need the mass or the radius of the object itself. Okay. All right. So what we're left with is this. GH equals 1/2 v squared plus 1/2 2/5 v squared. All right. And from there, we can then basically plug in the rest and solve for velocity. I mean, I just wanted to get you to that particular point. Okay. I want you to get to that particular position. All right. So, I mean, I'm sure this is again not worth remembering. There's no point in memorizing that formula. Zero point in memorizing that formula. All right, because what if I do a different object? It's not exactly going to be that formula. I don't know whether you can figure it out. What if I say this is a disk? What if I say I is going to be 1/2 mr squared? Can you recognize what's going to change? What's the only thing that was basically kept from I? The answer is the fraction. The fraction is the only thing that is left over from all the stuff, from I and from omega, after we basically break everything down. So we can now V, we can find V. We need the H. H is important, just like it always was when we were doing the old energy problems. We do need that height. That is important to us. But we can find how fast this object goes. In the end, if the problem does say what's omega at the end, then you can take your final velocity and divide it by r again. So maybe that is why they give you r, is that you can get the final rotational speed as well to help you out. Okay? The last thing I want to share with this is there are problems. Okay, I'm going to write out this last part again on the next page. GH equals 1/2 v squared plus 1/2 2/5 v squared. Okay. There are problems where they will say, what is the ratio of translational kinetic energy to rotational energy after it goes down an inclined plane like this? All right. And it's something that people sit there, and you can go ahead and go through the whole problem and calculate it all, but there's an amazing trick to find this answer by just looking at one formula. Okay. Basically, it's related to us getting down this point. So this is important. So, I mean, this trick comes from the point that we break the problem down to this final formula of GH equals 1/2 v squared plus 1/2, whatever the fraction is. I'm going to just say whatever the fraction is in front of I times v squared, okay, is what that's going to come down to. What we can do, amazingly, is what you need to think about. We can find this ratio very, very quickly in this formula. This section right here is basically referring to translational kinetic energy. This section right here is related to rotational kinetic energy. Okay? What is the only difference? Again, it's the fraction. We're saying, let me be very clear about this. I am basically saying the kinetic energy translational is related to 1/2 v squared. That's what the translational kinetic energy is related to. It's not equal to that because the actual kinetic energy is 1/2 mv squared, but it's related to that. Therefore, the only thing that I've added in, because let me rearrange this. This is 2/5 1/2 v squared. So what is this? What is it telling you about the rotational kinetic energy? It is 2/5 that of the total kinetic energy. It is 2/5 of it. All right? It is 2/5 of that point. So the ratio is the fraction. Okay? If I have it written out this way, where I'm relating translational to rotational, this is saying that the translational is 5:2, because that would be the fraction. I mean, this is in front of the rotational point. If I move it over here, I basically have to flip it. Okay, is what I'm referring to. All right, I need to multiply it by 5/2 is what I'm saying, because then it cancels out. It's 1/v squared again, if that makes sense. Okay, so the ratio is related to the fraction in the rotational inertia. Now, if I did say, what's the ratio between rotational to translational, that is the fraction. You write it out exactly like the fraction. So a common error is, and on the test, they'll give you 2:5 and 5:2. You need to make sure you're reading the ratio correctly. The rotational should basically always be less than the translational if we have a fraction. It's the fraction amount of it. If you're asking for the opposite, you just basically take the reciprocal. So for example, if instead I use a disk, if I said the inertia of a disk is 1/2 mr squared, and a disk, a round disk, it looks like a ball again, but let's basically say it's not a sphere anymore, okay? It's a disk rolling down, so it's thinner along the top. What would be the ratio of translational kinetic to rotational kinetic? The answer would be 2:1. It's the 1/2, I just reciprocal it. I reciprocal. What would be the ratio for a hoop? A thin hoop, the formula is mr squared. That would just be 1:1. There's no fraction, so we don't worry about it anymore. Okay? So that's a kind of a crazy trick that you could use to either solve a multiple choice very quickly You can relate, you can talk about that in terms of a good justification. All right, you might need to, unfortunately, if you have to justify it, go all the way through and show the formula sum as well, where it's coming from. But that is something, especially for multiple choice, to answer a question very, very quickly. All right, so that's it. Thank you.